And welcome back everyone to the history of mathematics. As you can see, Sophie has gone back to her usual napping spot in the closet. And we are going to get back to working on chapter 10 or 11. I think it's chapter 11. I'll feel better if I look. It's actually chapter 11 of Stuart Hollingdale's book, Makers of Mathematics. And the topic of discussion in this chapter is the work of Gottfried Wilhelm Leibniz, one of the co-creators of calculus. And as we discussed in a previous video, his name is attached to the so-called Leibniz rule, sometimes called the product rule. But what I wanted to talk about in this video was Leibniz's work with series. So there are a couple of series that we're going to talk about, and one of them leads to a very interesting, somewhat surprising approximation for the mathematical constant pi. So let's switch over to the document camera and look at that. So Leibniz and series. Now, when you're working with series, there are very few infinite series. Maybe I'll squeeze that in there. Naturally, if it's a finite series, we can just add up the terms and get the value of the series. But there are very few infinite series where that's the case. One of the exceptions is an infinite geometric series. Now, you probably remember from your calculus, or you might even have covered it in a course on algebra, but an infinite geometric series is where you get from one term to the next by multiplying times the same thing over and over again, and that is called the common ratio. And you probably remember that this series, 1 plus r squared plus r cubed, going on like that forever, converges to the value of 1 over 1 minus r if r is between -1 and +1. So that's one case where we can actually find the value of the series. We can plug in this formula. You might remember from calculus you have a lot of convergence tests. For example, the comparison test and the ratio test and the integral test. Those will all tell you that the series converges. They will not tell you what the series converges to. They won't give you the value that the series converges to. Whereas in the case of a geometric series, as long as r is between -1 and 1, the series converges to this value. And the other special case is what we'll call a telescoping series. And as we work out this example, I think you'll understand why these get the name telescoping series. So we're going to consider this series here. 1 plus 1/3 plus 1/6 plus 1 over 10. The next term would be 1 over 15. Okay, so the denominators are what are called triangular numbers. So the first triangular number is 1, and then 2, or then you add 2 to that to get 3, and then 6. And then the next triangular number is 10. And then if I added a row of 5 underneath it, I would get the fifth triangular number, which would be 15. Okay, so that's what we're adding here. The reciprocals of triangular numbers. And what we need to notice here is that the terms can be split up. So in other words, if I took this it's actually equal to this over here on the right-hand side. I can break the fraction up into a difference of two fractions. And that means that our fractions can also be split up. And I've got the arithmetic over here, right? To do the subtraction, I would need to get a common denominator. So this first term would need a factor of k plus 1 top and bottom, so it's right there. This would need a factor of k in the top and in the bottom, so that'd be right there. If I distribute and then deal with this, the 2k that I'm getting from here and the minus 2k would cancel, and it would leave me with a 2. So this fraction really does break up, like this right here. Now let's go and see the significance of that. So if I'm looking at this series, the series that goes 1 plus 1/3 plus 1/6 plus 1/10, etc. Well, we just said that we can split those terms up, and if I expand the series out using this formulation, well, when k equals 1, that's 2 over 1 minus 2 over 2, which is right here. And then when k equals 2, that's 2 over 2 minus 2 over 3. When k equals 3, 2 over 3 minus 2 over 4. Okay, now, the thing to notice here is that the second term here will cancel out the first term here. And that will happen all the way down the line. In fact, the only terms that won't get canceled were the very first one and the very last one. So now you can see why this is called a telescoping series. Now, the reason that's kind of interesting is knowing that we can say that this infinite series we can say that that series converges, and we can figure out what the series converges to. Okay, so of course we remember an infinite series is actually a limit of the sequence of partial sums, but we know what the partial sums look like. So this is really limit as n goes to infinity of 2 minus 2 over n plus 1. And of course, as n gets large, this second part is going to get smaller and smaller. Of course, that part's just going to stay at 2. So this infinite series converges to 2, and we can find the exact value that it converges to because of the telescoping nature of the partial sums. So it's a very neat little process to use. There is one other thing I wanted to consider here, and that is, it's actually one of my favorite problems that introduces students to working with series. Okay, so what I want to do is I want to consider this series. N equals, let's go ahead and make it 0 to infinity of x power n. Okay, well, x to the 0, of course, we know that's 1 plus x squared, so n equals 0, n equals 1, n equals 2, n equals 3, and we could keep on going like that forever. It's an infinite series. Okay, well, if you remember from just a few minutes ago, this is a geometric series. The common ratio is x. Okay, so we can actually find the sum in that case. It's 1 over 1 minus x. There is a restriction, of course. That only converges for x values between -1 and +1, but for any x in that range, the value of this infinite series is given by plugging that value of x into this expression right here. Okay, now the reason I like to look at this example is this function is equal to this series right here. Okay, well, let me think about this function, 1 over 1 plus x. Okay, very similar. The only thing I did was I replaced x with negative x. Okay, now, if I replace x with negative x in this expression, and this expression is equal to this series, that would be equivalent to replacing x with negative x in my series. Okay, now you'll notice it's every other term that gets a minus sign. And of course, we've got to take those instructions that I just said literally. I'm replacing x with negative x. So instead of x squared, it's negative x squared. And that, of course, means negative x times negative x. The two minuses cancel each other out. And you get a positive. So all the odd powers of x would get a minus sign, whereas the even powers would have a plus sign. Okay, so 1 over 1 plus x is given by this series right here. Okay, well, let's continue kind of playing this game and getting new series for different functions. 1 over 1 plus x squared. Okay, well, think about the change we just made. I took this expression here and I replaced x with x squared. So if this expression is equal to this series over here, I'll play the same game. I'll replace every occurrence of x with an x squared. Okay, notice what I've got here, x to the fourth. If I take x squared and I square it, because I'm replacing the x with x squared, so it should be x squared squared. Rules for exponents say that should be x to the fourth. And this would be x to the sixth, and so on down the line. Okay, so that is what this function would have as its power series. Okay, so you probably remember from your calculus coming up with all these power series. Well, there's a lot of fun manipulations you can do with these series. Okay, now I'm going to sweep a little bit of something under the rug here. The step I'm going to do actually does work, but there is a consideration that I'm just going to ignore for right now. I'm interchanging two limit processes, but you can go ahead and forgive me. Okay, so let's say I did this to both sides, right? If these two expressions are equal, it makes sense that their integrals are equal. Okay, so integral of this left-hand side would be equal to the integral of the right-hand side. Okay, well, this is a bunch of powers, and we can just integrate them using the power rule. Integrate 1, and you get x. Integrate x squared, and you get 1/3 x cubed. Integrate x to the fourth, and you get 1/5 x power 5. Integrate x power 6, and you get 1/7 x power 7. And that would continue forever. Okay, now we actually know what this integral is over here. Okay, so since this integral, 1 over 1 plus x squared dx, is something that we know and remember from our calculus, it's actually equal to the inverse tangent, or sometimes called the arctan. Okay, since that's true, then we know the series for tan inverse. Tan inverse of x would be x minus 1/3 x power 3 plus 1/5 x power 5 minus 1/7 x power 7 plus dot dot dot. Okay, that would continue forever. So we actually have a series for the inverse tangent function. Now you might say, okay, well, that's nice, but who cares? Okay, well, here's the reason I wanted to talk about this. If x equals 1, we're talking about tan inverse of 1, so I'm replacing all the x's with 1's. Okay, so I've got this right here. Tan inverse of 1 would be 1 minus 1/3 plus 1/5 minus 1/7 and so on forever. You get an alternating sum here on the right. They're reciprocals of the odd numbers. Okay, now we actually know what tan inverse of 1 is. Okay, remember your trigonometry, right? Trigonometry is dealing with the SOHCAHTOA, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we're talking about an angle whose tangent would be 1. That means the opposite and the adjacent sides would be equal. So you've got a 45-degree angle, or in radians, pi over 4. Well, that's what the right-hand side must be equal to, because that's what the left-hand side is equal to. So this infinite series, alternating reciprocals of odd numbers, should converge to pi over 4. Okay, and this is a series that Leibniz actually worked out. He used a slightly different method than what we did right here, but the punchline remains the same. So we have a nice little series involving pi that involves the reciprocals of the odd numbers. Okay, so in fact, between the last chapter and this chapter, we have two very elegant little approximations for pi. If you look back to John Wallis's work, you'll see he had an infinite product for pi where you had evens in the numerator and odds in the denominator. And here you have that right there, Leibniz's approximation for pi. So that's something that I think is a lot of fun. I really think it's a good introduction to working with series. So what you're doing is you're starting with some basic facts that you know about a geometric series, and you kind of apply some changes. You do the same thing to both sides in each stage. So certainly it would seem like we're keeping equality the whole way down, and you end up with that very surprising, in a lot of ways, series that approximates pi. Now it happens that that series that we just found, right, this one right here, that series for pi actually converges very slowly, and we'll talk about that in one of the exercises, but it does get you a series for pi. So that is one of the things that Leibniz is remembered for, that series approximation for pi. So that's all we're going to do in chapter 11. There's tons of other stuff you could do about Leibniz's life and work, but we're going to move on to chapter 12 on Leonhard Euler, and we'll put a link to the first Euler video down here. You'll notice that was a rather long derivation, and Sophie is completely knocked out over there on the filing cabinet. So, we'll see you in chapter 11, or chapter 12. We're in chapter 11 right now. See you in chapter 12.